Yeah.
Okay.
Yeah.
Okay, well, it's my pleasure to welcome today Surendra, who's a PhD student at Penn State University. Today, the talk is going to be about the symmetry and memory in rheology of non-Brownian dense suspensions. So first of all, welcome again to be here today, and thank you, Surendra, for accepting to give a talk. Surendra, maybe you can start sharing your slides. And in the meanwhile, you can give us a bit more insights about your background. What did you study? Where did you study? And stuff like that.
Yeah, for a fun fact, I actually, in the earlier part of my PhD, I used to work on, okay, this slides are going, sorry. Yeah, in the earlier part of my PhD, I actually used to study astrophysics. And one reason I actually liked astrophysics is how multi-physics and multifaceted it is. But then I really, didn't have that touch, to the reality. And I was looking around and saying, what other field has similar themes of, being multifaceted in multi-physics? And I've realized that soft matter is such a field where a lot of things come together to make you understand even the simplest things. And I realized the beauty in it, that even simple systems can hold really complex ideas. So yeah, that's been me. And before that, uh, it's always been astrophysics, and it's only in my PhD that I shift in my midway through my PhD that I shifted to soft matter. And ever since, I've just been working on non-Brownian suspensions, and which initially I thought this is a boring system, but as I got to study it, I've realized that it holds a lot of nuances. Yeah.
That's a very nice description of the whole subject. Thanks.
Yeah.
Okay. So Surendra likes to get questions during the talk, so people just raise your hand or feel free to interrupt kindly Surendra during the talk, and he's gonna answer your questions. The floor is yours.
Okay, thank you. So today I'm going to talk about two concepts that are, been studied in literature to some extent. One is about a particular symmetry in a non-Brownian suspension, and the other aspect is memory. Fascinatingly, non-Brownian suspensions can actually store and process information, and that's why we dub it as memory. And we're going to look at it more closely. And just to give an outline, I'll start with introducing my lab, and then I'll talk to you about why did we, I mean, in literature, people have already studied memories. Then why did we continue studying it, and what new things have we found, and where did we get the inspiration to continue working on it? And the third thing is I'm going to introduce kinematic reversibility and how it plays a crucial role in forming these memories. And then I'm gonna delve into what sort of memories do we see or do we observe in non-Brownian suspensions and how we can characterize them using bulk responses. And once we looked at the bulk responses, the obvious question that we rheologists always want to answer is how does what's happening in the microstructure that's enabling or causing this bulk response to appear? And then lastly, some implications or some conclusions based on this work, and then some future directions and recent work we have been doing past this. Yeah. So to introduce the lab, so I work at Penn State in Professor Nathan Kimes' lab. And as I said, I'm in my final year of my PhD. And besides me, a lot of my other group members also study memories in different systems. So we as a group, if we ever want to study memory, yeah, we are the ones, we are pros at it. So just to briefly introduce you to a couple of systems that we study. So this is my system where we have a rheometer and we use a concentric cylinder geometry, which I'll get into more. But besides that, we also study shape memory polymers. Like people are familiar with shape memory alloys, but turns out there are shape memory polymers too, which return to their state, this initial state when they're actuated. And we also study, how uh, memories can be stored in a jammed solid, a 2D solid that's shown here. Uh, and then we also study memories in contact lines. Like we basically have a contact line that's situated between two parallel plates. And then we drive this contact line with injecting some fluid and extracting some fluid out. And even this contact line, which is pretty ubiquitous, can also actually form a memory. Uh, and then here is a recent work that one of our postdocs did, which is about a tape, a typical tape that you see every day in your life. Even that stores some form of memory. So as you can see, we actually deal with a breadth of systems, and we study memories across all these systems. And the goal is, in the near future, we want to see what principles of this information processing and storing across the system are universal, and if they are universal, why are they universal? Like, none of these systems are really near criticality, so you can't really expect this to be a critical phenomena. Like, it's like, these are all way below criticality, but they still show some universal behavior. So why do they show, and what universal behaviors they show? And in fact, recently, that's in my next slide, which is the inspiration. As you know, there are different types of systems in nature which can store memory, like going from a simple vinyl disk to an SSD or a hard drive to even living systems like, say, rats and humans. Uh, and the way this information is stored and processed, like, say you take a vinyl disk or an SSD or a hard drive, you really don't want the multiple things that you stored, multiple pieces of information that you stored. You don't want them to overlap, right? Because they want to be stored, you want them to be isolated, because if they overlap, it leads to data corruption. So we don't want that. It's not a feature we want them in these systems. But if you go to living systems, there every day we see, we get exposed to something new, or some new memories come and they override some old memories, or some new memories comes and they make some of your old memories enhanced, just because it either validated, or it did not validate your previous conceptions. So there's always this interplay of memories of multiple kinds and multiple types in our human brain, in living systems typically. So we want this in a living system. Turns out there are non-living systems as well, where this is actually a feature, where having this interplay between memories can actually lead to functions instead of something, a feature that we do not want, like an SSD or a hard drive. So that's where the inspiration started coming in. And to before we go beyond that, I just want to show you a video. Maybe people are familiar with this. So here, a person is inserting some dye, a red and a green dye, as you can see. And this is also a double cylinder geometry. And he shears it in a certain direction. And you can see the dye particles are spreading out along the flow. And just to give you some details about this particular fluid in there, it's highly viscous. So, like, it's essentially a non-Brownian system where, and he's also sharing it very slow. So it's Reynolds number flow, and there is no diffusion, no such things. And as you can see, as he reverses the flow, the two droplets almost seems to come to the same initial configuration as they were. So this showcases one of the key things that we know from Stokes' flow. Stokes' flow says that if your viscosity is very high and there is no diffusion, your flow is essentially reversible. And this is a beautiful experiment that showcases that there is, in fact, kinematic reversibility, and it can be observed in nature, and you can actually showcase it, and that's what it shows. Okay. Now coming to my system, which has similar properties, like it's a non-Brownian suspension made out of particles, and it has a volume fraction of around 30%. And the particles are density matched to the fluid, so that the density difference between the particles and the fluid is very low, on the order of 10 power minus 4. So there's almost no sedimentation. And even if there is sedimentation, it happens on timescales of months. And whatever driving we do in the system is also laminar. Like, we do it so slow that it's laminar, and the viscosity is high enough that the Peclet number is very high. So this tells us that whatever driving or whatever dynamics that we observe in the system is the sole result of a driving, but not due to diffusion. And there are people have been working on trying to figure out what is the effective viscosity of this suspension? Like, and people have come up with different expressions, but one canonical expression is this, where the effective viscosity of the suspension depends upon the fluid's viscosity multiplied by some factors which depend upon the particle fraction. So as you may guess, and this expression holds in the dilute limit, like up to till 30-40%, but beyond 40%, this expression doesn't hold. But below that, we can actually use this expression to better understand how changing the particle fraction and particle positions can actually affect your effective viscosity of the suspension. So as I said, like the previous system also had laminar flow. It also had negligible diffusion, and even there the density was matched. So you would expect that even this system would showcase kinematic reversibility. So to look at it more closely, we uh, I refer to some work in literature where they've actually imaged the suspension, and they looked at the particle positions. And this was the basic setup. Like, you have the inner cylinder, you have the outer cylinder, and then the fluid is inside in between this gap. And then we dye the suspension by mixing a rhodamine 60 with the fluid, and we send in a laser sheet so that there is some fluorescency, and you get this green background, and then these particles appear as dark spots, and then we place a camera and then we image it. That's the basic setup. And if you observe, this is how it looks. Like, say you can rotate the inner cylinder and the outer cylinder is fixed. And as you oscillate the inner cylinder back and forth and you observe the particles, this is how they look. Okay. This is not so interesting. Like, it almost seems like the particles are coming back to their original positions. So, and we cannot really track each and every particle to see if they're really coming back to their original positions, as was shown in the video. So to do that, what we do is instead we do stroboscopic imaging. So where we actually take an image at the start of a cycle, and then we take another image at the end of the cycle, and then we compare the positions of all the particles at the start and the end of the cycle and see how much is the particles displaced. And this is what you get. And as you can see, if the particles are not moving at all stroboscopically, all these particles will be fixed in their positions. But as you can see, they're moving. So what does this tell us? It tells us that once you apply a shear cycle and then you come back to the original position, the particles are not coming back to their original positions. So why? So one question to audience is that, why is that in the context of dice and the previous experiment I showed you, we observe kinematic reversibility, but even this system has similar properties as, laminar flow and high Peclet number, but it still shows irreversibility. Yeah, and that's an open and long-standing question as to why, this system, although it has similar properties as the other one, still shows kinematic irreversibility. But this kinematic irreversibility is what actually enables the formation of memories. Honestly, if it was reversible, this system wouldn't have been interesting. But the fact that it's not reversible is what makes this system actually have or store information. Okay. What information can it store? The first thing that it can actually store is memory of direction. And to showcase that, what I'm going to do, I'm just going to show a simple protocol that showcases this, where we apply a steady shear in a certain direction. And as you can imagine, we rotate the inner cylinder in a certain direction, and then we observe the viscosity. And more or less, as you expect, the viscosity more or less remains constant. And if you keep shearing in the same direction and you observe the viscosity, and again, it more or less remains constant. But say you shear in one direction and then you suddenly reverse the shear direction instead of following the same direction, but here you went in the opposite direction and you observe a sudden drop in viscosity. So it's almost 20% reduction in viscosity. And in a way, we can say that the material remembers that it was actually sheared in this direction, in the counterclockwise direction to begin with. And if you keep shearing in the counterclockwise direction, you don't see any difference. But if you shear in the clockwise direction, you see a sudden drop. And a little preview into microstructure as to why is this happening? Like, why does the system remember the direction it was sheared in? Turns out when you shear the suspension in a certain direction, it and you look at the G of R of the microstructure, and this is what you get, where it actually shows. So when you shear a suspension, it has two axes. One is called a dilation axis, which is this, and the other is called a compression axis. As you can imagine, when you shear a box into a parallelogram, uh, along this direction, particles tend to move away because of the dilation, and particles tend to come together in the compression axis. And turns out, if say you start with an isotropic suspension and you shear it in one direction, it sort of forms the structure. Like, I'll not go into details as to why it forms structure, but if anyone's interested, we can talk about it. Uh, but it forms this structure where there are more particles along this direction compared to the this direction. So in a way, this anisotropy in the microstructure of the particles is what encoded the information about the direction. And if you keep shearing the suspension in the opposite direction, and as you can see, the system eventually becomes isotropic in the opposite direction. But if you keep shearing the same suspension in the opposite direction, you can see that now the structure has flipped. Like earlier, the structure was in this direction, associated with this direction of counterclockwise direction. But as you keep shearing in the clockwise direction, the structure flipped. Like it initially got destroyed and then it got flipped, and now it represents the other direction. So the memory of direction is essentially embedded in the microstructure of the particles. And here, the other thing that we observed in our own experiments is that the bulk responses at higher strains, like as you go to higher and higher strains, eventually in the opposite direction, the study value of the viscosity should reach the same study value viscosity as it was in the other direction. But here you see there's a small discrepancy, and this discrepancy is because of viscous heating in our system. And to remove that, we normalize the viscosity by dividing the viscosity with respect to the steady state viscosity. So moving forward, you'll always see viscosities around one or less. Okay, so in a way, you can say that this initial study shear is the writing part of your protocol, where you can write a memory, and then you can read the memory using these protocols. So, like, when you store some information and when you use a protocol to store some information, it always has to have two things, like, a writing part and a reading part. Okay. Once you've written, if you can't read it out, it's useless. Yeah. Okay. So now we ask a question, like, what if we introduce an oscillatory shear in between, right? Like you start with a steady shear, followed by an oscillatory shear, and then you follow with a cup, and then you have two choices for your steady shear. You either go in the same direction as your initial preparation direction, or you go in the opposite direction to your initial preparation. And then we keep asking questions, what happens? Again, but now your writing part has become a bit more complicated. Your writing doesn't just involve a simple study shear, but it also has oscillatory shear. And the readout remains the reading part of the protocol remains more or less the same, where you have two choices for reading. Either you can read by going in this direction or in this direction. So, but you're adding a new piece of information by introducing this oscillative protocol. Honestly, you're actually adding two, which is the amplitude of oscillative shear and frequency of oscillative shear. But since we're doing everything in laminar flow, like, very slow flows, the frequency of the driving doesn't matter. And the only thing that really matters is your amplitude. And we'll come to see how amplitude of the oscillative shear matters. So now we have two pieces of information when you're writing it down. One is the direction, and the other is the amplitude of your driving. Okay, and this is how the final protocol looks like. You apply a steady shear in one direction, followed by an oscillatory shear, and followed by a readout either in the same direction or in the opposite direction. Okay, and now let's look how the responses, the bulk response of the suspension look like. Okay, so you apply a steady shear, followed by an oscillatory shear, and then you do a readout, and this is what you get. Okay, and instead you go in the opposite direction, this is what you get. And okay, the discrepancy between the red and the green response can be attributed to the anisotropy in the microstructure that I just introduced to you. You can say that the reason why these two responses of the suspension are different is because, uh, this initial studies shear sets up a direction, a preferential direction for your readout, where if you read in the same direction as your initial preparation, you get a stronger response. But if you read out in the opposite direction, you get a weaker response. So this is an artifact of memory of direction. Okay. So now if you actually take a first derivative of these two curves and you plot it, this is what you get. Like, you get a peak of right around zero point 0.6. And you also take a derivative of the green curve, you get a peak right around zero point 0.6 again. And guess what? The amplitude of your oscillated driving was zero point 0.6. So your system not only remembers memory of direction, but it also remembers memory of amplitude. Okay. After this, the next thing we started observing is, here I'm showing you two protocols, like a response of from two protocols, like where you can see initially the red and the green curve, the difference between the response is high, but here the difference between the red and the green response is small. Like, it's almost like these red and green curves are coming close together and becoming more or less the same. So what did we change to get these two different responses? The thing that we changed is the training amplitude of the oscillator shear. Like, we kept everything the same, and the only thing we changed is the oscillator shear. And here the amplitude was zero point 0.7, and here the amplitude was 1.4. So we asked, like, okay, so if we keep increasing this amplitude of oscillatory shear, do these protocols become same? Like, do these responses become same? Okay. So to answer that question, we introduce a new quantity called delta, which measures the asymmetry of these two responses. In a way, you're seeing how asymmetric is the red response from the green response, and the delta essentially captures the area between these curves. And as you can imagine, when this red and green curve overlap and they become the same, the delta would be zero, right? Okay. So what we did, keeping everything else constant, we just increased the training amplitude, and then we monitored how does delta vary with gamma t. And this is what we observe. Like, as you keep increasing gamma t and you observe delta, it goes to zero actually. So what does this tell us? It tells us that, the green and the red response have become the same. Okay, why is it that important? So turns out, non-Brownian suspensions always carry the information about their recent direction of driving, but we have found a way to erase that information. So in a way, we have actually erased memory of direction using memory of amplitude. So the delta means that whether you shear in the forward direction or in the backward direction, you're getting the same response. Your red and your green curves are the same. It means that your suspension no longer remembers, or the microstructure no longer remembers whether, one direction or the other. So that's the beauty of this point here. It's showing you that you can actually use the protocol that enables memory of amplitude to erase memory of direction. Okay, so what if you keep continuing to do this? And we actually observe that it rises up, the delta increases. And so here what's happening is, initially the memory of amplitude was erasing memory of direction or suppressing memory of direction. But as you go to higher and higher amplitudes, your memory of amplitude can no longer erase, or it can no longer suppress memory of direction, and this memory of direction pops back up again. I'll go into details as to why this is happening, like what's happening on the microstructure, or what at least what we think is happening on the microstructure that's causing this interplay between memory of direction and memory of amplitude. Yeah. Okay. And the other thing is, curiously, the strain at which this zero happens, this delta equal to zero happens, also correspond. Like, we asked, is there something special about this amplitude where is memory of direction is suppressed by memory of amplitude? Turns out there is. It's actually in the neighborhood of something called a critical strain. So turns out I'll show you in a bit in a while. The suspension actually undergoes phase transitions. It has two phases called a reversible phase and an irreversible phase, or they're also dubbed as absorbing phase and diffuser state. And the suspension can actually transition from an absorbing state to a diffuser state. I'll explain in a bit more detail as to what these states are in a little while. But the amplitude, the critical amplitude at which the suspension transitions from an absorbing state to a diffuser state is your gamma c, and that gamma c. Okay, someone has a question.
I do, but I
Uh,
mean, please finish if you want, you can finish this your sentence. I don't want to interrupt. So
Yeah. So turns out the amplitude at which this memory of direction being suppressed by memory of amplitude is the same as the critical amplitude at which the system uh, you know undergoes phase transition from an absorbing state to a diffuser state. Yeah.
so practically what you're correct me if I'm wrong. You're showing that the oscillatory you're doing is more or less depending on the amplitude of the oscillation, erasing the memory of the previous steady shear, right?
Yeah.
Um, so so you've shown the effect of the amplitude. Have you studied also the effect of the frequency?
So I did vary the frequency, and as I said, since as long as you stay below the Reynolds number equal to one, there is no dependence on frequency.
Okay.
Uh, but if you go beyond Reynolds number equal to one, yeah, there would be some dependency on frequency, but it will no longer be systematic.
And so you do you stay in the linear regime with
Yeah, yeah,
okay, perfect. Thanks.
yeah. Okay, and this gamma c, like what it also implies something else, like when your system is at when you apply a strain value of gamma c, your system actually goes towards criticality. And it's a well-known thing in the field of physics, that when systems go to criticality, they lose any and all information about their initial conditions, like they become critical. And one such state, like critical state, the suspension goes to, is called hyperuniformity. And this has been shown in literature that when system becomes hyperuniform, it doesn't remember anything about its past, uh, because everything in the suspension is every particle in the suspension is essentially interacting with everything else. Uh, but we still think, like, even if your system is hyperuniform, even if your system is critical, there could still be some structures, some major structures that survive this criticality or this hyperuniformity. And these major structures can actually represent certain initial conditions about your driving, like, whether it be memory of direction or memory of amplitude. So we need to do a bit of imaging to further answer this question, whether the reason why the system becomes symmetric is because the system has reached the critical state or this hyperuniform state, or is it something different? Maybe it's not hyperuniformity, maybe it's something different. So that's a question we're going to ask very soon. We're going to answer very soon. Okay. And so this is a similar plot I just showed you in the earlier slide, but here I've added a different like where I'm comparing two different protocols. Look, so if you look at the green or the sine curves, the sine data points, I was comparing the response of this protocol and this protocol. But if you look at the purple data points, I'm actually comparing this protocol with this. And the difference between these two sets of protocols is that the first protocol is the same, but then the second protocol that you're comparing the first protocol against, that's where the difference comes in. So here you see that your end of the oscillator shear and your readout are in the same direction. But here, the end of the oscillator shear and the readout have a discontinuity here. And we think that this discontinuity is what makes the memory of direction pop back again. But if you actually don't have the discontinuity, and if you have the end of your training and the final readout in the same direction, you can see that the delta goes to zero and it remains at zero and it doesn't pop back up. So we think that this discontinuity there is what causes the new, the memory of direction to pop back again. Okay. So just to give you, some background, like what's happening on the, I just give you a little, I did give you a little preview in the context of memory of direction as to what's happening to the microstructure. Okay, so what enables memory of amplitude then? Why does the system remember the amplitude of its most recent driving? So let's get into a bit more details about the microphysics of this, and we can relate it to the bulk response to the microstructure. And just to, again, this is the same imaging setup that people have used in literature that I showed you earlier. And so a couple of, I'm going to explain what a diffuse state and what an absorbing state is. So what's actually happening here is, say you start with an initial distribution of your particles, they're just randomly placed in your suspension. And then you keep shearing the suspension and you observe stroboscopically what's happening to these particles, right? And you monitor something called fractional particles moved, and that's the quantity that's being plotted here on the y-axis. Not sorry, fractional part, but it's the uh, mean square displacement of the particles. And here you can see that for gamma not equal to 1.2, for an oscillator shear of 1.2, the system found an absorbing state. So your mean square displacement of your particle goes to zero. But there is a different state that the system can reach at a different training amplitude, or at a different amplitude, 1.8, where the system found a diffuse state. Okay, this still doesn't completely give you a physical picture of what a absorbing state versus a diffuse state is. Let me show a couple of movies. So this is where a system finds an absorbing state. So initially you have particles and they're all interacting with each other, and you keep shearing them, and these particles are self-organizing, they're moving away, they're displacing themselves, and eventually they find this absorbing state where they no longer interact with each other. They no longer interact with each other, and that's an absorbing state. But this is a diffuse state. Like even here the particles are interacting with each other and displacing, but even after multiple cycles of driving, the particles never really self-organize to move any longer. So this is a diffuse state and this is an absorbing state. And the amplitude at which the strain amplitude of the oscillator shear at which the system can no longer reach an absorbing state is the critical amplitude. And once they do reach, the absorbing state, this is how the particles look. So once you reach the steady state and you further drive the system, right, and you stroboscopically image them, you can see that the particles' positions are not really changing. But if it found a diffuse state and you further drive it, the particles will still keep moving. So just to summarize, initially you start with an initial configuration of particles, you drive the system, and the particles are interacting with each other, either hydrodynamically or by contact forces, and they're self-organizing, and they reach this absorbing state where they no longer interact with each other. And if you further drive the system doesn't change. It essentially remains the same. But if the system reaches a diffuse state, they will still keep moving around. Yeah. And as I said, this actually showcases a phase transition where if you go keep below a critical amplitude of gamma c, the system, for no matter what your training amplitude is, or no matter what your amplitude of your oscillator shear is, the system always finds an absorbing state, but it may take more and more cycles to reach this absorbing state as you keep increasing the amplitude of your oscillator shear. But once you go past the gamma C and you go to higher amplitudes, no matter how many cycles of shear you apply, it will never reach an absorbing state, but rather it reaches a different state called a diffuse state, where the activity has decreased compared to the initial state, but there is still some activity that survives even after subjecting it to multiple cycles of driving. Okay. And in fact, people have actually proposed a very simple kinematic model to explain what's being observed and try to simulate this. And the simple kinematic model that captures this, like a lot of qualitative features of what experiments have observed, is you have a box and you have some particles inside it, and you apply a shear to the box, and then you see what particles have overlapped when you shear the box. And then say if these two particles overlap, you subject these two particles to random displacements in the reference frame, and you keep doing this again and again, like you keep cycling through this, then eventually even the system reaches an absorbing state and diffusing state based on the amplitude of your oscillator shear. So these were the simulation results, where you can see that for a low enough amplitude of oscillator shear, the system reached an absorbing state. But for a higher amplitude, the system reached a diffusive state. And just like experiments, even simulation show this phase transition, where if you are below gamma c, your system always find an absorbing state, but the number of cycles to reach this absorbing state depends upon your amplitude of oscillator shear. But once you go past the gamma c, it's again diffuse states. And looking more closely as to what's happening, during this driving, like instead of looking at the movies, say if you plot fractional particles moved stroboscopically, like you see how many particles moved at the end of every cycle. So at 0 cycles, you have a lot of particles that move, but as you go to 100 cycles, you can see that the fraction of particles moved has gone down, and you sort of see this kink forming. And that's right around your training amplitude, which is 3 here. And as you can see, as you keep driving the system and as you keep subjecting it to more and more amplitudes, you can see that eventually the system, the particles no longer move, or they no longer interact with each other for all amplitudes that is smaller than the training amplitude, or the amplitude of our oscillator shear. And once you go past the amplitude of your oscillator shear, they will start moving again. And in fact, you can actually store multiple memories, like memories of multiple amplitudes in your system, by doing a protocol where you have a larger amplitude followed by a smaller amplitude, like two different amplitudes, and you can actually store multiple pieces of information. Like, this kink corresponds to the lower amplitude memory, and this kink here corresponds to the higher amplitude memory. Okay. So why is this happening? Like, why is it that this system shows kinematic irreversibility? Like, when you subject the suspension to cyclic driving, like, when you shear the suspension back and forth, why don't the particles come back to their original positions? Like, yeah, eventually, once they reach this non-equilibrium steady state, they do come back to their original positions. But after just one cycle of driving, they don't come back to their original positions. Why is that? The question and the answer lies in the roughness of the particles. So there have been multiple experiments in literature where they showcase that the origin of irreversibility as to why these particles don't come back to their initial positions after one cycle of shear or a couple of cycles of shear is because of surface roughness. And to showcase that, what they have done, there's this beautiful experiment by Popova et al., where they have this geometry, which is a essentially a cylinder, and then you have an inner cylinder and an outer cylinder, and they place these two particles, uh, which and they're at different radii from the inner cylinder, and then they shear this and they observe what happens to these particles. And what they observed is that the center of mass of these particles, or essentially these two particles, tend to move away from each other. And they've also changed the roughness of these particles, and they saw that, okay, if the particles have higher roughness, do the particles tend to move away a lot more? And that's what they observed as well, that if you actually which is the bead blasted here, which has higher roughness, these particles tend to move away from each other. So essentially what I'm saying is the reason why the particles, why there is irreversibility in the system is because these particles under shear flow are interacting with each other, and due to surface roughness, they move away from each other. But then when you reverse the flow, they're not coming back together again. Yeah. Because there's nothing that would try to come back, that would try to move them together. Okay. So some implications for memory based on all the studies we did is, uh, so say you have this protocol of oscillating shear, right, where you have a red and a blue part of the protocol, where you have the positive amplitude and the negative amplitude. And as you can see, the positive amplitude is different from the negative amplitude. And say you apply a study shear like this, like you apply study shear, your initial study shear in this direction, followed by an oscillatory shear, followed by a readout in this direction, you actually read the memory of the positive turning point, which is here. But if your initial preparation is in this direction, which is in the opposite direction of your final readout, even then you see the memory of the positive turning of the positive amplitude, but it is suppressed because of memory of direction. And if you instead do your readout in the opposite direction, you observe the memory of the amplitude memory of the negative amplitude, as you can see here. But if your initial preparation is again in the opposite direction of your final readout, the memory of the amplitude is suppressed because of memory of direction. So previously, literature told us that when you apply a protocol like this, the only thing that the system remembers is your training amplitude. But now we know it actually remembers not only so we call this positive amplitude also as the turning point, because this is the point where the inner cylinder turns around in direction. So it not only remembers the memory of your positive turning point, but it also remembers the memory of your negative turning point. It also remembers the information about whether your study share and the readout are in the same direction or in the opposite directions. And it also remembers whether you match the end of your oscillatory shear and beginning of your readout, or the end of your study shear and the beginning of your oscillatory shear. So a lot more information can actually be stored in extractor than meets the eye. So your microstructure of the suspension can actually remember a lot of information about the recent flows that it is subjected to. So memory of amplitude and direction coexist. We erase the memory of direction using the memory of amplitude. The dilute suspension is more symmetric, but only at the critical amplitude. But the reason we all think that this is all possible is microstructure. Everything lies in the microstructure. And there are 2D jam systems that showcase this similar interplay, like, of memory of direction and memory of amplitude. So the question comes about, is this a universal feature of every non-equilibrium system out there, which can store and process information? So just a brief, a revisit to the inspiration that I initially talked about, how. So here I'm showing you a couple of videos. Uh, okay. So on the left, you actually see that there is a rat. Uh, and okay, so this is just an experiment that's done by neuroscience people, like where they actually wanted to see how does short-term memory work in rat's brain and human's brain. And to do that, what they do is actually there is a pre-stimulus delay, like where they wait for the rat to come into position, and then they apply a stimulus, right? So the rat has whiskers on the right side, on the left side, right? Uh, and here, what they do is they have a vibrating tip that vibrates at a certain amplitude, um, or at a certain strength of stimulus, and then it vibrates the tips of these whiskers. And after that, they have a small delay, and they follow it by a second vibration, and they ask the rat, okay, is the second vibration stronger or weaker than the first vibration? That's the basic question they ask the rat. Like, it has to use some sort of strategy to figure out whether the second stimulus that it was given is stronger or weaker than the first stimulus that it was just given. And based on whether it predicts it right or wrong, so uh, there are rewards as it's shown here. So a left reward and a right reward. And this rat is deprived of water, so it's very thirsty and it really wants to drink. And based on whether the second stimulus is stronger or weaker than the first stimulus, the reward is on the left side or on the right side. Say, for example, if the second stimulus is actually stronger than the left stimulus, the reward is on the right. And if the rat uses the right strategy and predicts that, hey, yeah, the second stimulus was actually stronger than the first stimulus, then it should go to right so that it gets its rewards. So in a way, we're actually asking, what strategy does the rat use, and uh, how the short-term memory, like, and another example I can give you is, like, say you go to an optician, right? And he asks you, like, is this lens better than the previous one? Or is this lens worse than the previous one? For that, you should be able to hold the information or the memory of the previous lens that was shown to you. And you would need to make a comparison. So in a way, there is this new information coming in and override and comparing against the old information. And there is this sort of an interplay which I'll not go into details, but we are actually collaborating with some people from the neuroscience lab in Italy and from CISA, and we're writing up a paper and showing on how the strategy that the rats and humans uses and the principles behind the strategy are actually very similar, or can be very similar, between a non-living system and a living system. Like, even in the non-living system, you have multiple memories of the same kind and different kind being stored, right? And they're competing, and they have an interplay between each other. And we're asking the question how this interplay between these memories in a non-living system can be very similar to a living system. So what's happening next? We're actually taking it two-dimensional. So far, the driving was, only it was in one plane. But now we're actually going to apply a shear in the orthogonal direction as well. So you essentially have a three-dimensional or a pseudo two-dimensional shear. And then we're going to ask a question, can the system still remember information about both of its drivings? Not just the oscillator shear in the plane, but can it also remember the driving that's orthogonal to that plane? And the other thing is, so far I've shown you protocols which are symmetric, yeah. But what if it's random, right? Then can still the suspension remember some information about this random driving? If it can, what information about the random driving can it actually remember beyond, say, the amplitude of its driving? Okay, even if it can remember the amplitude of your driving, what amplitudes among these multiple amplitudes that are available, what amplitude will be stored? Yeah. And how do the other amplitudes in the random driving actually affect the amplitude uh, of the value that's stored? And we've also started imaging, where we've actually made a transparent coat cell so that we can closely look at how this microstructure changes during the protocols that I've showed you, and try to explain what's happening on more clearly, or, like, instead of uh, basing on it on literature, we want to do our own experiments and try to explain why does this interplay between memory of direction and memory of amplitude come about, and how does memory of direction being suppressed by memory of amplitude, like, essentially, what is happening to the GFR, what is happening to the measure structures. So that's the question we want to ask. And we recently put out a paper based on this work. You can check it out on arXiv, and we submitted to PRL recently. And I'm also on the lookout for postdoc opportunities. And that's my email address. And with that, I thank the organizers for this opportunity, and I'll take any questions.
Thank you. Thank you so much for the very nice talk, Surendra. Okay, then question time. Do we have any question from anybody?
I do have one question. Um, well, I was wondering about the signal. If you have put like a really weird one, if it will show the memory of that weird signal, but you already teased about it. So I have another question. You said also in your conclusion that you can see those memory effects on the jam system. Did you try with another volume fraction, or did you try something else, or is it just a hint, or?
So we did actually try it at a different particle fraction. I don't have the plots to show, but I can tell you one thing, which is, where is this? Yeah. So as I said, gamma C depends upon the particle fraction. Like, as you
Mhm.
increase the particle fraction of a system, this gamma C changes.
Yeah.
Uh, a- yeah. And so the reason why these purple dots goes to zero at a different gamma value compared to this cyan curves is because this cyan has a different particle fraction compared to the purple data. So for the cyan curves, this was
Hmm.
this like so we did these experiments to collect these purple data points 2 months before we did the experiments to collect the data about the science. So between these 2 months, the system had actually sedimented a little, and the particle fraction has actually increased a little. And because
Okay.
the particle fraction increased a little, the gamma C of the system has actually decreased a little. So this is how we show that you know the whatever we observe can actually depend upon particle fraction. Like as you vary the particle fraction, the qualitative features may remain same, but the places where this delta goes to zero, that can depend upon particle fraction. So I
Mm.
guess what I'm saying is, in the continuous limit of, going from phi equal to 10 to phi equal to 50, you will still keep observing this interplay of memory of direction and memory of amplitude. Uh, but the values at which, say, the strain values at which the memory of direction is suppressed by memory of amplitude will change based on the particle fraction. So that's one way to probe the role of particle fraction.
Okay. I
And
thought that at some point it will be like so messed up that you could not reach this kind of value, but okay. Okay, okay.
no, 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 that is true too, right?
Okay.
So if your particle fraction is very high,
Mm-hmm.
then your gamma C will be very small, so it won't be able to reach the steady state. Yeah.
Yeah, okay. Okay, very nice. And when you will do the also you will do also the shear like in the other direction. I don't even know if you can see me, but I'm doing stuff with my hands.
I can
Um,
see.
yeah, okay. Whenever you will do that, and if you have a high volume fraction, you will have also some moment where you have your particle that's gonna have like they're gonna go on each other and you're gonna have maybe this dilatation moment where they all stack up and then they go back. And don't you think that you're gonna have other how do you say that, other response that actually are not gonna be easy to detect from your stuff? Will you be able to still get your memory effect, or don't you think that you're gonna have other physics going into play that's gonna be difficult to understand at the end? Or did
Yeah,
you already go through it? Yeah.
yeah, a couple of things. Actually, I'm showing you that it's a little preview, but we have already done a bunch of experiments on this, and
Okay.
but we have always kept the particle fraction low enough. Like we never really
Yeah.
went to 50% or 45%. We've always kept it below 35% or 30%,
Mhm.
so that whatever effects you're saying don't come into play. And in
Yeah.
that, yeah, yeah, that's what we did. We control the particle fraction and we made it low enough so
Low
that we
enough to
don't,
kind of avoid those things. Okay,
yeah.
I see.
But eventually, we are interested of increasing the particle fraction and going beyond and seeing what the new physics comes in, and then can memory still survive in that new physics as well? Yeah, that's a question we're asking as well. Yeah,
Okay. Well, sorry, I
and
have is there
yeah, and
other
just to
question?
tell
Oh, there are
people.
other, yeah.
Yeah, I was going to say, just to tell people what we've actually observed is that just like how memory of direction and memory of amplitude can actually coexist, uh, in these experiments, we've actually observed that memory of this direction of driving and the
Mm-hmm.
memory of this direction of driving can actually survive together. Yeah, it's almost like, you have this like, essentially these memories are being stored in positions of the particles, but you only have a finite number of particles in your system. So you can imagine that you can only store finite amount of memories at the end of the day. So you have
Mm-hmm.
a capacity. like a limited capacity. And within this limited capacity, sometimes one memory just uses up the whole system, and you can no longer store any other memory. Or it can be that one memory uses only a few percentage of these particle positions, so that there's still some left in the budget, and it can store a different memory. So that's what we think is what's happening, because earlier we thought that maybe this is some sort of nesting, but as you can imagine, we're not going in and placing these particles carefully. We're just driving them. So when they self-organize and when they interact with each other, they randomly, like these particles, like this memory information is stored randomly, in random particles in this system. So instead of nesting, we actually think that maybe, maybe these two particles here and these two particles here store the information about this direction of driving, and maybe these two particles here and these two particles here store the memory of the other direction, or a different kind of memory. That's what we think is happening,
Mhm.
at least in this context. Yeah.
There's another question. Riki, you can go for it.
Yeah. Hiya. I'm experimentalist here, so sorry, I don't kind of like follow along well with kind of like shit a lot of parameters and simulations. So when you talk about the particle fraction, are you talking about the volume fraction or the particle size itself?
Volume fraction.
Volume fraction. So basically you're saying this whole thing, basically you simulated it in a diluted system, right?
Yeah. Up
And part
till 30%, 35%. Yeah.
Okay. And particle size wise, what limits we're talking about?
They're millimeters, so not like around 100 to 100 micrometers.
100 microns. Okay. So in a real life setting, where do you think this whole thing can be used? Because I'm thinking like mixing apparatus, for instance. So how this knowledge basically can be beneficial further down the line.
Yes, so far we haven't really thought about that, because we have only been focusing on the neuroscience aspect of it. Like, what sort of protocols do they use in cognitive neuroscience to study short-term memories? And if we can replicate those protocols in the non-living systems as well, and then see how these memories can have an interplay. But beyond that, I have come across a couple of papers where they try to show that in industry, it's a well-known thing that people, I don't remember the exact reason, but for some reason, people really don't want the suspension to remember the recent flow history.
Hmm.
And there's always been a question as to how do you make the suspension, a non-Brownian suspension, or a similar system of a kind, uh, to not remember any information about this flow history. And in a way, we're answering that question that, hey, if you go to these high enough strain values of you know of around 1.8 or something based on the particle fraction, uh, you can actually make the system forget about any of its recent history.
Or increase the temperature. That'll do it.
Yeah,
Cheers, thank you.
Why?
because there would be diffusion, and the diffusion would kick the particles out of their positions, and
That depends on the particle size.
yeah, it depends on the particle, but it can, maybe it's not possible every time, right? Maybe some people want to maintain the temperature because they don't want to affect the solvent's viscosity, or they don't want to change the sizes of the particles, because there are some particles where the size of the particles can vary with temperature. So temperature is not always a solution, but I agree that it can be a solution sometimes.
Yeah, because you're basically simulating or trying to kind of like introduce some order into disorder kinetics. And
Yeah.
basically you can go both ways, either by increasing the shear or increasing the temperature or lowering them, of course. Thank you.
Well, one of the what you were saying, Surendra, is very true. So, for example, when you when people do, for example, oscillatory shear experiments, I mean, in general, practically, whenever you do experiments under the rheometer, you wanna erase memory from the loading, for example. So you don't want your loading protocol to influence the measurements you're going to do. And one thing is doing steady state shear, for example. You just wait for a long time and hope that you're just so far that you erased everything that happened before. But when you do oscillatory shear, for example, you really want to make sure that you start always from the same starting point microstructurally wise. And so, for example, from one protocol that's been around for some time is you just load your suspension and then you start oscillating with a very, very big amplitude. And then you just decrease the amplitude and you just go down to very small amplitudes. In that way, you just span the whole spectrum of amplitudes and you practically make sure that you erased all the previous microstructure that you may have enabled during contact. So yeah,
Yeah,
that's
but yeah, but one thing I want to point out is it doesn't really take a lot of study shade in one direction to really create this anisotropy in the microstructure.
sure. Yeah.
Yeah. So that's always been a trouble. Like, some people, they really don't want this anisotropy in their suspension, but it's always there because you cannot avoid it. Like even a little bit of study shear in one direction can actually, yeah.
Absolutely. 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 Okay. And well, I don't know if you I'm sorry if this I mean, I don't know if you already answered the question I'm gonna ask. Maybe you did, but sorry if I missed it. But have you measured how many cycles do you actually need to like what's the minimum? I mean, is there
Yeah. So that, yeah, that depends
is
upon the,
is there a rule of thumb, for example, that one has
yeah,
to
yeah,
follow?
yeah. So that depends upon your amplitude.
Hmm.
Uh, so at low enough amplitudes, you can just use 10 cycles, for example,
Okay, so
like
it's yeah.
around 10 cycles. But as you go to higher and higher amplitudes, you need more and more cycles to form an amplitude memory. Yeah.
Thanks. Okay.
But typically, it's more or less around 10 cycles. Yeah.
Okay. Any more questions? If not, I think we can call it the end. Well, thank you, Surendra, so much again for a very nice talk. It's been a pleasure and it's been very, very interesting. And thank all the audience for being with us today as well. And hope we'll see you all together in 2 weeks from now. Thanks.
Thank,
Mm,
thank you.
thank you.